So this talk relates a bit to the first talk because it's also about instance segmentation. But in this case, we're interested in segmenting the vertebra. So I'd like to motivate that first a bit. Vertebra segmentation is useful for a number of automatic spine analysis tasks. For example, most common, I think, is compression fracture or fracture detection and fracture classification. But also assessment of, for example, spinal deformities like scoliosis, or also planning of surgical interventions such as screw placement. Vertebra segmentation is basically not just a segmentation, but an instance segmentation problem, because for most applications, it's not sufficient just to differentiate between background and vertebra or vertebral bone, but we also need to differentiate between the individual vertebra. So any generic algorithm for this problem shouldn't make any assumptions about how many vertebrae are visible, especially because the spine is visible in a large number of different types of scans. For example, spine scans, where we see then really a large part of the spine, but also in, for example, chest CT scans, where we see only a small part of the spine. So we should also not assume which vertebra, so anatomically speaking, which of the vertebrae are visible, and we should also not assume where in the image they are located. Because, for example, a spine scan would be focused really on the spine, but a chest scan would be not. So from not making any of these assumptions, some challenges arise. One of them is really the field of view. So here you see an example of a spine scan of the lumbar spine and of a chest scan. You really see that the spine scan is focused on the vertebra. That's the main object of the scan. And in the chest scan, there are a lot of other organs also visualized. The second problem is that we cannot use very simple post-processing steps to separate the vertebra. If you look at this low-dose chest CT scan on the right, you see that some of the vertebra really, there's no border in between anymore. You can't really separate them by doing something like a connected component analysis or so. This can also be the case if there's some pathologies. Like in this case, you see here some bone formation. So then the vertebra can actually grow together, or the gap can be very small. So what we tried first is kind of the obvious approach. There are usually 24 vertebrae in every human being. So you can just train a segmentation network with a multi-class output and just try to segment the different vertebrae. So in this case, we tried to train a 3D UNet on this, which surprisingly works well in many cases, but in some vertebrae, the results are not very plausible, so it's confused which vertebra this actually is. There are some instance segmentation approaches in the computer vision literature. These are just some of the ideas. The first one is maybe the most intuitive one, to work on defining a loss function that forces the network to segment different instances. This is actually a paper that one of the reviewers pointed us to, where they try to not really assign a label to each pixel, but to assign an embedding vector to each pixel, and they force then the embeddings of different instances to be different from each other. So that's, I think, quite a promising idea. There are also other pipelines that are usually based on detection and segmentation steps. For example, the well-known mask RCNN, where basically first the bounding box is detected, and then the segmentation within that bounding box is performed. There are also ideas that are based on recurrent attention. So that relates a bit to the talk before this one, where then LSTMs are used, and then one instance is segmented after the other. So if we look at the segmentation problem of vertebra, then we can actually realize that vertebra segmentation is not really a generic instance segmentation problem, but a restricted problem, because we have only ever one class. There's only one type of object that we're segmenting, not cats and dogs and many other objects. And we also know that the instances are not scattered around the image, but they're located next to each other, because together they form the vertebral column in the image. So basically, this is a binary instance by instance segmentation approach that makes a lot of sense, because then we can include all of this knowledge in the segmentation. So the idea of this approach is to segment instances one by one, and to use the location of the first instance to find the next instance, and so on. So in this example, the last lumbar vertebra is first detected, and then in the next iteration step, the vertebra above this is detected, and so on, until all vertebrae are detected. And this essentially then combines detection and segmentation in a single step. But if this network needs to remember between iterations which of the vertebrae are already detected, so it should either be a recurrent network or have some kind of memory component to remember this information. So the network architecture that we use for this is basically inspired by U-Net. So this path is essentially a 3D U-Net, and then there are some modifications that we made. First, so the I stands for the image that is fed as a 128 by 128 by 128 patch to the network, and the output is then the segmentation mask. And before the segmentation, we have a sigmoid because, as I said, it's a binary problem in this case. So we do not assign different labels, but we really segment current instance or everything else. So it's a 1-0 output. And the segmentation has then a feedback loop to this M, which is the memory component, which is basically just the binary volume of the same size as the image, in which we mark all the voxels that have been segmented before or have been assigned to an instance before. Additionally, there's a classification output, but I will come back to that later. So this is just an outline of how this works, because it's actually patch-based, so the images are usually larger than 128. So if we have a patch, we extract the same size patch from the memory and feed both to the network. So they're just concatenated. It's a 2-channel input then. And the desired output is then the first visible not segmented instance. That can be done from top to bottom or from bottom to top. That just depends on how you train the network. In this case, it's then from top to bottom. So the desired output, here illustrated as the ground truth, is really only a part of the first visible vertebra. After that is segmented, it's added to the instance memory. And in the next iteration, this is already supplied to the network. So the network should realize that this instance has been segmented and should focus on the second instance, and so on, basically. Additionally, we use then this information that instances are located next to each other in the image to avoid really classifying the entire image again and again and again, because the individual instances usually make up only a small part of the entire image. So what we do is we travel through the image in a sliding window fashion until the first instance is found, and then we search in the neighborhood of that instance for the next instance. So basically it's a search and track strategy that we use here. So this is an illustration of this. First, the patch or the region of interest moves over the image. The blue box is here the patch, and the blue arrow is the direction where it's going to move for the next iteration step. And at some point, it will segment part of an instance. So usually, it will not immediately find an entire instance. So the first vertebra will not be entirely contained within the patch, but part of it. And the strategy that we use then to switch from sliding window to following the spine is we calculate the center of the patch or the fragment that it found. And the next patch in the next iteration is centered at the center of the fragment. So in this case, the patch moves to the center of the red part here. And then we just feed the same, or the patch at the new location through the network again. And at some point, the entire vertebra will be visible within the patch, and then the patch stops moving. So it kind of converges. And at that point, we check off this instance added to the memory and continue. And because we know that the individual instances are really located close to each other, and because the field of view of the patches is large enough, we simply classify the same location again. But the updated instance memory, now containing this instance, forces the network then to detect part of the next instance. If it would, in some cases, not detect anything, it would just go back to a sliding window way until the next instance is found. So the same principle continues then, so it again is centered at the next fragment, until all of the vertebrae are segmented. You have an animation of this. I don't know if the box is visible. That's the region of interest, the red box that's moving over the image. Here it finds then the vertebra, and then it starts really climbing along the vertebra until all instances are found. And then it continues as a sliding window, and at some point it stops because it reached the end of the image. So now this classification output. So usually the UNet is interpreted as a feature extraction path and then really the segmentation painting path. So we add the classification output by continuing from the features to really just a single value with the sigmoid unit in front. And the reason for having an additional classification of all the instances is that if we have scans that do not contain the entire spine, some of the vertebra might be incompletely visible in the image. And that can be a problem if we automatically want to calculate some kind of features, biomarkers, like calculate the height of the vertebra or something like that. Because then we would derive these biomarkers from incomplete instances and they would just be incorrect. The reason why we not just ignore these instances, so train the network not to segment those, is that basically we need the first instance to start the traversal process. Tried that also without that, but then the network, the performance is worse because it always sees some part of unsegmented vertebral bone and the traversal process does not start properly. So in terms of loss function, we just use a combination of two terms for the segmentation and the classification. The classification error is just the binary cross entropy. For the segmentation error, we use something that's basically in between a cross entropy and the die score. It's just the sum of false positives and false negatives. So basically, we just minimize all the segmentation errors. And that worked better in this case compared to die score because it doesn't contain the number of true positives. And for this traversal process to work, we sometimes have to feed completely empty patches to the network so that do not contain any vertebra at all. If you then have the number of true positives in there, you get very spiky loss curves, very different gradients at that point. So these are then similar to the die score soft implementations or probabilistic implementations of false positives and false negatives. Like in the original UNet paper, we use also a weight map to give more weight to voxels at the boundary of vertebra. So that really helped a lot to improve the segmentation accuracy between different instances. More training details, we use the Atom optimizer with a high momentum because we can fit only a single patch at a time into the memory of the GPU. We forced every 6th patch to be completely empty. And during training, we do not build up this memory, but we just infer it from the ground truth segmentation. For evaluation, we use two data sets. One is a public data set from a challenge at MIGCAI 2014. That's 15 spine scans. That's quite an easy data set for spine segmentation because those are all healthy young adults. And it's quite a high resolution data set. To make it a bit more challenging, we used then also low dose chest CT scans. For those, we had 15 that we manually segmented and 20 scans where we trained the network on the validation set and then corrected the segmentation masks that it produced. And those we used only for training. And these are a bit more challenging because of the low contrast, because of low dose artifacts, and also because the section of the spine that's visible can differ quite a bit. So these are the spine CT scans. For this case, we trained the network to traverse from top to bottom. So that's also why the colors are different here, but it always starts with the same color. And there we really had no problems at all with the segmentation, so quite good results. If we look at low-dose chest CT, in this case we trained the network to go from the bottom to the top. And maybe you can see that some of the vertebrae are a bit lighter. Those are the ones classified as incomplete. I think in this case there are no mistakes. The segmentation masks are also quite good. Maybe you can see some minor results, minor errors. Those are also reflected in numbers. So if we look at the SpineCT data set, then we achieved a really high DICE score of almost 96%. And especially compared to the challenge winner, we improved quite a bit in the average surface distance, even though that method was already quite good. Because always almost the entire spine was visible, so all thoracic and lumbar vertebra, there was only one direction of the spine where vertebra could be incompletely visible. And the network got, in this case, all of these cases right. If we look at the low-dose chest CT data set, we can see that the performance is a bit lower, which is, I think, totally expected. Still quite high performance. There were some mistakes with the classification, but we also have almost 96% accuracy. We tried to see whether the slice thickness, so basically the resolution of the scan, has an influence on the result, but we actually found that it performed better on thicker slices. But yeah, just a minor difference. So in conclusion, 2 main points. I think the most interesting finding from this is that we see that fully convolutional neural networks can also learn more complex tasks, like taking an additional memory input and inferring from that which part of the image to focus on. And that this iterative instance segmentation approach is effective for spine segmentation or for vertebra segmentation in all kinds of tomographic scans. So thank you for your attention.
Thank you. Questions? Yes.
Very nice talk, thank you. My question has to do with abnormal spines. So in the setting of either a compression fracture or a degenerative disc disease where the gap between the vertebral levels is absent, what would happen?
Yeah, so that depends a lot on the training data, because this is, of course, a fully supervised approach. Initially, we tried to apply the method trained only on the healthy data set, on a data set with compression fractures, and then you see really that it has problems with these kind of vertebra. But when we train it with these are, of course, more challenging cases, so I expect lower results, but it ultimately depends a lot on the training data, and there's nothing that limits the network from, or that makes the network fail in any case. If the training data contains these examples or similar examples, then there's nothing that prevents it from working.
And the ribs touch the vertebral levels. Does the segmentation ever catch ribs by accident?
No, not really. So there can be like minor inaccuracies, but not that you really find part of the ribs or so. Really at where the ribs connect to the vertebra, there can be small mistakes, but not, really the ribs are never segmented, basically.
Thanks.
More questions? Maybe first here and then.
Have you considered? Have you considered doing multiple passes, like say from the bottom and from the top, and then resolving their predictions?
I've not tried that, but I can imagine that this would be helpful in a couple of cases. For example, sometimes it can happen that at the bottom only a very small part of vertebral bone is visible, and that it doesn't pick that up, or it doesn't pick it up correctly. So if you would do multiple passes, you could maybe even that out, or fix these mistakes.
So you have some sort of ordering in your detection. Let's say if you have 3 spines, you are first detecting the first, and then second, and then the third, but at each time you are ignoring the other 2. So my question is, do you experience some difficulty because your model is kind of a spine detector, but you are ignoring the other 2, for example? So do you experience like some discrepancy, or your model does it well because of the memory you have?
Yeah, so in most cases this works well, but the problem with this is that that basically the last instance segmentation depends on all the previous instances. So in some cases there have been these mistakes that when the network is not fully converged and I try to run it already, that it segments half of a vertebra, and in the next iteration, then yeah, it really starts to fail because the instance before is not completely segmented, so it's not completely excluded. But in cases where the segmentation is correct, it really learns very well to use this memory input to completely block out all other instances and completely disregard those.
You mentioned that it worked better for thick slices. Did you do any statistical significance tests on that?
No, so I can imagine that this is probably not a significant difference, also because these were 10 test scans. So in a larger set, I can imagine that it will also look the other way around.
Think we can do one more question? I have one. It might happen that in some cases, I think you can have a patch where one instance is segmented, but two of the next ones are visible. Would the method work successfully in that case also?
Yeah, so that can indeed happen. The method, so what I see from experiments is that the method really looks either at the bottom or the top of the patch. So those are really these cases when you have a scan where very little of the first bone is visible. So there's basically a threshold that says what the minimum fragment size is. And sometimes this very first fragment is too small. And then the network gets really confused what to do because it sees there's vertebral bone. So it always really looks at the first instance that's visible. So if they're too visible, there are usually not really problems with detecting both. It really looks for the first one and finds that one.
Well, let's thank Nicholas again and wish him a happy birthday.